Over the years, Lee College of Engineering robots have accomplished a variety of tasks. They have scaled inclines, climbed stairs, unscrewed bolts, navigated obstacles, moved weights, and deployed bridges. But no matter what their function, they have all had the same purpose: to develop and test the design skills of mechanical engineering students in the William States Lee College of Engineering. They are the hands-on robot projects of junior design. Known officially as MEGR 3156, junior design is the midpoint in the mechanical engineering design sequence. The objectives of the robot projects are to test the students' engineering knowledge, design ability, innovation, teamwork, project planning, and construction abilities. The lead teacher for junior design in 2006-2007 was Dr. Kevin Lockett.
The specific purpose of junior design is for students to apply topics that they have learned from the sophomore courses, which include statics, solids, basic electrical, and also machining practices in manufacturing the robot. The project for this semester is a mobile mini bridge, and the students are required to have a robot, and this robot must traverse over obstacles that are no larger than a standard 2x4, ascend a 30-degree incline, and then deposit a lightweight bridge across an 8-inch gap. They must disengage from the bridge, drive across it, turn around, return over the bridge, and finally return to the original starting spot and volume. The culmination of junior design is the competition at the end of the semester. Some of the teams will get done early and be fully prepared and ready to go. Other teams will not be quite so ready and will generally stay up the whole night before preparation, trying to be prepared for the competition.
The junior design semester starts with a series of lectures on design issues. The teams are then assigned and given the criteria for the robot project. The first deadline for the teams is the preliminary design presentation. At this midpoint, they must give a formal presentation that outlines their design concept, calculations, work plan, and cost estimates. Once they can show that their robot will work if built to specifications, the teams are given the go-ahead to proceed to the construction phase. Starting at this initial construction phase in the spring of 2007 was Team 7, which was made up of juniors Brandon Ring, Audrey Stanley, David Reinhardt, Jason Romaine, Jessica Spannell, and Patrick Simpson. The team began its work on a powerful robot design that would use 5 motors, as explained by Brandon.
Our robot is based off a chassis which is 4 by 7 inches. We will have these motors, which we will attach hubs to the end and the wheels will attach to the hubs. We will have a motor set on the front of the chassis and a second one attached to the back of the chassis, kind of like that. And at the same time, we will have a 5th motor, actually. This thing will mount on top like that. And the 5th motor, which is our bridge actuator motor, will sit on top just like that. All right, so if you can picture it, you have the motor and the wheels right here. You have the bridge actuator motor right here. And then in all that, the bridge will sit on top. And all our circuitry, which we are working on right now, will fit all right in here below the height of the tires and above, well, below the bridge, but above the chassis. So it's going to probably look something like that. The reason why we went with 4 motors instead of just what most teams do, just use 2 motors and then have a chain drive to the other 2 motors, is one, it'd give us a little bit more torque, a little bit more power, and if one motor breaks or fails or we strip one gear, we still have full control from the other one.
Along with the project specifications for size and function, another part of the design criteria was that a number of the parts must be made using a rapid prototyping machine. Leading Team 7's rapid prototype construction was Audrey Stanley.
One of the design requirements for our project is a rapid prototype wheels that will get us over the obstacles. So we designed a wheel that will be 4 inches in diameter, so we'll have about 1.5 inches clearance over the obstacles. The first step in prototyping a wheel is to design it in ProEngineer. After we design it in ProEngineer, we bring it into a program called Insight, which allows us to generate the toolpaths for the rapid prototyping machine. This is the Prodigy Plus by Stratasys. It is one of 2 rapid prototyping machines that we have in Duke Centennial Hall. Basically, it has a printer head that lays down layers of plastic on this foam board, and it builds it up layer by layer. Any parts that have overhangs that need support, it'll lay down support material for it, and then we can clean that off. After the printer head lays down a layer of material, the platform will move down, and then the printer will continue to lay down material until it's finished the part. By using this machine, we can test a design and see if it will work before we mass produce it. If we need to make changes, we can come back and make them within several hours instead of several days. For our junior design project, we're going to prototype 3 components. We're going to prototype 4 wheels, a circuit box to enclose all of our circuitry, and a controller.
The second deadline for the teams was the Subsystem Trials. At this point, bridges had to be complete and were tested for strength and weight. The bridges with the best strength-to-weight ratios scored the most points. During the Subsystem Trials, the teams also had to demonstrate the workings of their electronic control circuitry. Upon completion of the trials and approval of the systems, the teams could go back to work.
We're about 1.5 weeks away from the competition now, and as you can see, we finished our rapid prototype wheels. We added a hub and also a hub cap that covers up the screws and the nuts, just for aesthetics. We also finished the top of our controller, and as you can see, this just came off of the prototyping machine. The blue material is the modeling material, which is our actual part, and the brown material is the support material. You just break the support material away, and whatever remains you can soak in a solution and it will dissolve the remaining support material. So far everything has come together pretty well. The only major issue we've run into is the fact that our chassis was too wide. We had to narrow it a little bit. We also removed a little bit of material in the middle so that we could have a lighter chassis. Lighter robot means faster time.
So we're about 4 weeks into the project, about 1.5 weeks before we actually have to complete the vehicle. Last time you saw it, it was a solid metal chassis. Nothing was cut out here. We didn't have the bearing blocks mounted, we just had them glued. So since then we have permanently mounted the bearing blocks, attached the wheels, and removed material on the chassis so that it's lighter, plus we also had a cardboard box on the top of the chassis which was housing our circuit. Now we actually have our circuit box housing all our circuit stuff with our on-off switch, our tether wire terminal, and we even went a little overboard and put a little 7. Well, 1 7 this way and then an upside down 7 on our box. So we're Team 7, that's why. So today we're just trying to mount the drivetrain, the circuit box, and the bridge actuator motor mount. And we want to mount all that together and hopefully by the end of the day be testing the drivetrain of the chassis, trying to go through the course, for most of it at least. We still have to make the bridge actuator arms and mount our fancy little bridge.
After a long semester of lectures, team meetings, design concepts, construction, presentations, and system trials, the day of the competition finally arrived. For some teams, it was a relief to reach the day they had been working towards. For others, who spent most of the night before fixing last-minute problems, the day may have come a bit too soon. For Team 7, they were ready.
It's April 24th, Tuesday, about 8:20 in the morning. We finished up our robot about 8 o'clock last night. Done a couple things. We've put a number 7 on the top of our robot. This is our new bridge that we wanted to build. And you can see it's got a little bit bigger of a spacing between the wheels as the previous one. And so far, we've been able to run it at a minute flat on the course, and we haven't had any major issues yet. I've seen a lot of good designs so far. Whether they'll work or not, we'll see. But I'm looking forward to seeing them all, and the best team hopefully will prevail. We've got to go weigh it in now, see how much we weigh. As far as measure the length, the width, and the height to make sure we're under the minimum requirements, which I believe we are. We've measured it several times to make sure, but we got to go find out. So.
Following the weigh-ins, the teams took to the track, with Team 1 up first. The hard work and design ability of the teams was clearly evident as the first few teams successfully navigated the obstacles, climbed the incline, deployed their bridges, crossed, turned around, and returned to the start-finish box. The strength of the teams made it quickly apparent that to win the competition, the top team was going to have to do more than just finish. They were going to have to post a fast time as well. Each team was allowed 2 runs. The prevailing strategy was to get a safe, successful first run that would secure a good grade for the class, and then, on the second run, to go for broken pride in trying to win the competition. With some good runs completed before them, Team 7's turn came. Brandon took the controls and started their 4 months of planning and hard work down the track. He made it quickly through the initial obstacles and up the incline. There was just a short bobble with the bridge, but the rest of the run was smooth. The team's efforts had paid off, as they posted the fastest first run with a time of 64 seconds. On the second runs, some of the teams began to get faster, while a few others who had failed on their first runs just tried to complete the course. On its second run, Team 7 posted another top time, this one at 63 seconds. At this point, the top 3 teams moved on to a championship round. The best time from this round would be the champion. With a few hitches in its final run, Team 7's time was 8 seconds slower than their best run. The other teams had improved, but not quite enough. In the end, Team 7's time of 1 minute and 11 seconds had won, nosing out the second place team by 1 second.
All right, we just finished the competition and we won.
Woo!
Hey!
We ran a minute flat in our trials yesterday, and our fastest run today was about 1 minute and 3 seconds. So we did exactly what we thought we were going to do. The robot came together really well. We didn't have any real problems with it, and we're very excited.
I think our biggest success was that we kept it simple, straightforward. We didn't try to do anything exotic or crazy like some of the other teams, which allowed us to focus more on making sure that our robot didn't break or didn't have issues with balance or friction, which I think may have ultimately led to us having such a successful competition. From this point on, it's up to Dr. Lawton what he thinks our overall grade is in the class. There's a lot of things that are going to be weighed, such as weight, cost, time that we actually put into the robot, and the way it performed in competition. So hopefully Dr. Lawton will give us a good grade. And we still got the final to take care of too, but we're almost done.
In the end, the robot projects had demonstrated a variety of design solutions for achieving the same task. Some had 2-wheel drive, and some 4-wheel drive. Some used DC motors, and some servo motors. Most achieved their objective of running the course successfully, and all of them achieved the class objective of developing the design, teamwork, planning, and overall engineering skills of the students. For Team 7, they had won the honor of being the fastest robot, and based on the total design criteria of weight, cost, and aesthetics, had been named to a tie for second overall by Dr. Lawton. The robot had now taken a place of pride in the display case as one of the year's best examples of the Williams States Lee College of Engineering's hands-on projects of junior design.